Okay. So since the plan for today is to go over Module 0, call it Module 0 because it's just the introduction to some of the interesting things happening in the field of solid-state electronics right now to get you interested in the material. And hopefully we will finish that by break, and then the second half we will start going into the class material, crystal structures in electronic materials. So before we do that, let's just, since we will start on the syllabus, we'll start on doing the presentations next Tuesday, we can talk a little bit about what the presentation is going to be about. So the presentation has to have it's going to be, I'm going to limit it to 5 minutes. Okay, that's not very much time, but I think we have to do that just to make sure that we get through all the course material. So there's going to be a 5-minute limit. So please make sure that you stick to the time limit. If you need to practice it a few times, then that's a good idea. 5 minutes will probably be anywhere between like 5 to 7 slides. Okay, you'll be doing your presentations in PowerPoint. Bring your presentations on a flash drive, and you can load it up on my computer here, and just run it from there. That'll save us time. Last semester, students were downloading it from email. It just took a little bit extra time. So just bring it on a flash drive, and we'll run it off there. Your PowerPoint files, please you can save it to my desktop. That way I have all the PowerPoint files for assigning the grades later on. There'll be 5 minutes for timing and 5-minute presentation, and then maybe 3 minutes question and answer, really 1 or 2 questions from the class. I do want all the class to participate, so during the semester, please make sure that at some point you have the opportunity to ask the speakers questions. And certain topics might be more of interest in you than others, so I don't expect you to obviously have questions for every speaker. So what is this presentation about? The spirit of this, as I mentioned in class last time, is to get you interested in a topic of your interest within the field of solid-state electronics. It can be anything of your choosing as long as it's related to solid-state electronics. That's going to be one of the things I'm looking for. The presentation must have a clear relation to solid-state electronics or device physics. The second thing is that the presentation must present some type of new or recent technology. New or recent, generally students have done one of 2 things. Either they talk about a new gadget or a new technology that a company is releasing soon, and examples have been OLED displays for cell phones, different types of biomedical sensors. Yes?
What's your definition of recent? Like past month, past 2 months?
Recent means the past year.
Oh, okay.
Yeah, past year is fine. The different areas of solid-state electronics we'll go over today, but some of the examples are display technologies, photovoltaics for solar, various types of environmental and biomedical sensors that use semiconductor devices. A lot of times there's interest in the semiconductor field, what the newest, latest and greatest is in terms of microprocessor performance, or different types of memory structures. Memories are also semiconductor devices. So that's just to name a few examples. So you should be able to find something either industry related, or even better yet, find some research papers. If you do a search on Google Scholar, and you do a search on a topic that you're interested in related to semiconductors, you should be able to find hundreds or thousands of papers on newest technologies. In addition to Google Scholar, last time I asked you in class, it seems a lot of you do read blogs, blogs and different types of websites. One of the ones I will suggest is EE Times. Let me write that up on the board here. EE Times, Technology Review. IEEE Spectrum. These are examples of a few different online magazines. But besides that, you can find a lot of new gadgets on things like Gizmodo, MedGadget. You know, these are more blogs. Now, if we look down here, part of the requirement for the presentation is that there should be sufficient resources, at least 3 to 5. Now, it's okay if one of your references is one of these blogs or an online website, but the other references should be something more substantial. It should be like some sort of an online journal or online magazine. Best is if you have actual journal articles that are in a peer-reviewed publication. Okay, there are many such journals. If you do a Google Scholar search, Google Scholar only searches peer-reviewed academic publications. Now, I warn you beforehand that some of those are a little bit difficult to read, but that's some of the work that will have to go into it. If you need help understanding an article, I'm more than happy to help you. Sometimes what will happen is you could read about a new technology in one of these websites, or there's many others such online magazines. They tend to describe it in a lay version that's easy for you to understand, easy for the class to understand, and that's essentially what you're going to present to the class. I want you to dig a little bit deeper so that you can answer everybody else's questions, so that you understand the material a little bit deeper. Look for the actual article that these things are pointing to. If this is saying like, okay, this was published in Nature Technology in this particular year, then you can go to that actual article and read about the actual thing there. Okay, maybe show some of the results that the authors found. A couple years ago, there was a publication in Nature on molybdenum, and it was showing that it's a semiconductor material that has mobility much faster than silicon, so that could ultimately lead to much faster microprocessors. So a lot of those types of research articles are published in high-profile journals that I would like you to find the references to. Again, if you have any questions about this, any questions or point of confusion here? Okay. So you use a combination of some of these online journals and then some of these online blogs, and then the actual academic source. Technical content demonstrating a thorough understanding of the presented material. It is only a 5-minute presentation, but I want you to understand the topic that you're presenting. Examples, I'll post today after class or tomorrow, I'll post a bunch of the PowerPoints of presentations that students did in past semesters to give you an idea, just the breadth of topics that are done. Okay, just to give you an idea of what I'm looking for. Quality and clarity of the presentation, it's only 5 to 7 slides, so you make the slides nice. Pictures are better than words. Pictures describing the concept. You're basically explaining a new concept to your colleagues in the rest of this class, and that's something that you're going to continue to do in industry or in your jobs. So just get used to that, sharing information, and it'll help everyone enjoy the class material more. And the enthusiasm of the speaker and the ability to answer questions. You're only going to have 2 questions, maybe 1 question, depending on how much time we have. But you should be able to address the questions insofar as possible. Okay. I sometimes ask questions to see if you understand the material well enough. And so, if you're able to answer the questions well and confidently, then you'll get additional points on that. The presentation is going to be 5% of your grade. And I usually just assign a number between 1 through 5 in increments of 0.5. Okay. Any questions on the presentations? All right, good. All righty then. Let me just make sure that this is closed. I should close this before. Oops. All right, so let's without further ado, let's get into the class material. Yes, let's do that. I think we can turn off one half of the lights here. Is that better? Good. All right. So, like I said, this first module is just an introduction. A few things about the class first. We went over the course details, the syllabus, and all the administrative stuff and the introduction. So now we're going to talk about motivation for studying solid-state electronics. Like I said last time, there's the preview of the course. We're going to talk first about semiconductor physics and phenomena and properties. So this is going to be the first half of the course. Can you all see this little pointer thing? Okay. A little bit difficult to see. Maybe I'll make this red. Okay. Well, all right. Okay. So the first half of the class is going to be in semiconductor physics, phenomena, and properties. So we're going to study a few important concepts. One is that the structure of a material determines its electronic properties. The second concept is that carriers are responsible for electrical conduction and charge storage. And the third concept is how carriers move to create current and store charge. So the first concept, the structure of a material determines its electronic properties. That's chapters 1 and 2. Okay. Now we're going to see that as just like in a mechanical material, the atomic structure of a mechanical material determines its mechanical properties. The atomic structure of an electronic material determines its electronic properties. There's something called the Schrödinger equation, which nicely describes that. Next. Then we'll talk about the carriers. There's two types of carriers in semiconductors, electrons and holes, and they are responsible for carrying electricity through a semiconductor. Okay, so we'll look at the physics of that, how they move to create current and store charge. So those are the two things a semiconductor does. They carry current and then they store charge. All of our digital computations and microprocessors are based on this essential concept. Second half of the class, we'll talk about semiconductor devices, PN junctions, bipolar junction transistors, MOSFETs, and LEDs, and so on. We may not have time for bipolar junction transistors this semester, as I said last time in class. So we'll see how that goes. So study suggestions, a few suggestions here. There are a lot of different concepts that we're going to be covering in this class. A lot of physical concepts, and then a lot of mathematical problems that you'll be doing. So my suggestion with this is to visualize qualitatively what's happening first, and then go to the equations. Books, a lot of engineering textbooks have a tendency to get right into a concept and go right to the equation and say, this is an equation describing the way that charges are moving in a semiconductor in response to an electric field. Okay, they'll have an equation that says the velocity is proportional to the mobility times the electric field and so on. Okay, if you go right to the equation and try to memorize the equations, chances are you're not going to understand the concept as well. The movement, I'll just give you an example here. The movement of carriers in an electric field. You guys remember this from physics? You have positive charges here and negative charges here. And if you place a charge within the electric field, the charge moves from positive to negative, right? And that's a concept that you all remember very well from physics. You remember, it's a visual concept that you remember in your head. Now there's also an equation that describes this, that the velocity is equal to mu times the electric field. There's also more complicated equations which describe the acceleration of the particle. So if you go right to the beginning and start memorizing the equations, then you'll lose sight of the concept here. Okay, this is obviously a simple concept, so and the equation here that I've written is quite simple. But when it comes to other concepts like carrier diffusion, where there's differential equations describing the phenomena, it's important that you can visualize the main concept, the way that carriers are moving in the device, and so on. If you have the qualitative understanding first, then the equations won't seem quite as overwhelming. Since we have a lot of concepts in the class, I suggest that you can categorize them, make outlines. In your exams, I allow you 1 page of notes front and back for the midterms, the 2 midterms that we will be having. And in the final exam, I allow you to have 2 pages of notes front and back. And what students often do is that they outline a lot of the main concepts in those study sheets. That's what I used to do a lot when I was a student. And writing outlines seems to help a lot, especially when there's a lot of concepts. Outlining concepts, drawing some pictures in there to help you remember the concepts, writing down equations. It helps you to synthesize the different concepts together. The other point here is practice, practicing and reviewing. I mentioned this in class at the end of class last time. I will be posting the homeworks online, and I'll also be posting the solutions to the homeworks online. The reason I post the solutions right away is because I want you to be able to have something to refer to if you're not able to solve the problem. There are a lot of students here who work, and it's difficult for them to come to campus. It's difficult for them to come to office hours. The homework solutions that I have, it kind of takes you through step by step on how to solve the problems. That being said, the number one mistake that students make in this class is just, before the exams, before the quizzes, they just quickly look over the homeworks and look over the solutions, and it looks, oh yeah, that looks pretty easy. And they all end up doing very poorly on the exams and homeworks. You have to struggle, like I was mentioning last class, you have to struggle through the problems. Do the problems on your own. Do not look at the solutions unless you've been working on the problem for more than an hour and you haven't made any progress. When you struggle through the problem and you're looking up concepts in the book, looking up things in the notes, that's when all the learning is really happening. Okay, so take my advice on this. If you want to do well in the class, make sure that you don't just use the homework solutions for a quick, to just quickly get through the homeworks. The homeworks will not be graded, by the way. They will not be graded. They will not be collected. They are just a means to prepare you for the quizzes and the exams. The quizzes that we will have are going to be based on the homeworks. So if you don't do the homeworks, or you just breeze through the solutions and you don't understand them very well, then you'll end up doing poorly on the quizzes. Last semester we had about maybe like 9 quizzes, one every other week roughly. At times it was like once a week. Okay, we'll do it depending on how much time we have in the class. Expect somewhere between 5 to 10 quizzes. Yes?
Are you going to announce them before we have them, or are they just going to be?
I will announce them before we have them. I'll announce them at least one class period in advance. So backing up here. I plan on spending about 12 to 16 hours per week on this course. As a 4-credit course, you can expect to spend 4 hours in class and maybe another 10 hours outside of class. This is just general guidelines. Okay, next. My teaching style is informal, and I want to have as much interaction with you all as possible. So when you have questions, actually you don't need to raise your hand. Just feel free to interrupt if you have any questions. If there's a concept that you don't understand. Another thing that happens often is that I'm going over something and I'm in my own space and I'm going over something relatively quickly because we have to finish this by the end of the class period. Okay, and sometimes I may end up going too quickly. I would like it to be your responsibility to make sure that if you don't understand something, feel free to tell me that, oh, can we go over this concept again? I don't get it. If you don't understand it, there's a very good probability that others in the class don't understand it as well. Okay, so please don't be shy in asking to revisit a concept or tell me that there's something that needs to be explained better. I will not take offense to that at all. There's no such thing as dumb questions. And so if you need extra help outside of class, I do have office hours 2:30 to 3:30 on Tuesdays and Thursdays. If you have any concerns about the class or about our curriculum in general, just do let me know. In terms of study groups, I mentioned this last time. One thing I could do is just simply say that if, before homework assignments are due, we could just say like our classes are 3:30 to 5:30, Tuesdays and Thursdays. So we could have a study group that meets 1:30 or maybe say 2 p.m., 2 to 3:30 p.m. And you can meet like right across the hall there in that little study room. So, it's informal. I mean, obviously you're not required to attend, but that can be a gathering place for students. Maybe an hour and a half before class if you want to have any questions on homeworks that you want to ask other students or work with other students. I found that usually after class students are pretty tired and they just want to get home. So let's have the time before class. If there's another time that anyone would prefer, like come talk to me at the break, and then we can set that up. Why is this moving forward on its own? That's why. Okay. A few things about why it's useful for you to take an undergraduate course in solid-state electronics. First and foremost, as an undergraduate in electrical engineering, you are expected to know how electronic devices work. Now, in Electronics 1, you build circuits out of different electronic components. You make the common emitter, common source amplifiers in Electronics 1 course, and then for those of you who have taken digital logic, you learn how to make a logic gate out of an NMOS and a PMOS transistor. Okay, so you're working at the circuit level, and in this class you're learning about how the actual devices work, how the NMOS and PMOS device themselves work, how the diode works. We're looking at the internals of those devices. Second thing is being able to understand the physical limitations and second-order effects in modern electronics. For example, CMOS, there's something called the short channel effect. The short channel effect makes it difficult to make transistors smaller than they are right now. Okay, and those kinds of things are very important to the electronics industry. For example, Intel, for many years, well, I'll show you a slide on that. We'll go into the details of that in a second. Number three is that there are newer emerging areas of solid-state electronics that require knowledge of device physics. Examples include photovoltaics. So solar cells is very important right now for getting solar energy. Nanoelectronics, new types of electronic devices that take advantage of low-dimensional electronic materials like nanotubes and graphene. Different types of biomedical sensors, different types of environmental sensors that use semiconductor devices. Another interesting area is something called organic electronics. Organic electronics are things like organic LEDs, OLED. You guys have all heard the term OLED TVs and OLED screens, though that's a newer area of solid-state electronics. So there's, I don't want to make any broad statements about this, but I would say like in the 80s and 90s, like it was all about the transistor, bipolar junction transistors and metal oxide, MOSFETs, the stuff we're going to be studying in this class, and diodes, a few different components. Now there's all sorts of electronic devices that are being used in consumer applications, different types of LEDs, different types of sensors, and so on. So there's more devices out there. You have to have a basic understanding of solid-state electronics, a semiconductor theory, to understand how these classes of devices work. I'll breeze through these few different things here. The first motivation, understanding electronic devices used in circuit design. So let's see this here. I guess this isn't working too well. There we go. Okay, so analog and digital circuit components. So we have the diodes, BJTs, MOSFETs, and JFETs. And there's also things like optoelectronic components, lasers, LEDs, photodiodes, and solar cells. These are all semiconductor devices. There's also, like, these devices can be implemented using different materials. For example, a lot of high-speed semiconductor devices that are used in your microprocessors are made from silicon. They're made from a material called silicon. It's a column 4 element. I'll get into that a little bit later. Other high-performance devices use things called compound semiconductors, gallium arsenide and indium phosphide. And then high-speed microprocessors also use materials such as silicon germanium. Then harsh environment electronic sensors use things like silicon carbide and even diamond. You can make electronics out of diamond. So just like any other engineering field, for a certain type of device, you need to choose the right material. So all these different types of devices can be made from these different types of materials. And I want you to understand how these different types of electronic devices can be designed, including the material properties, including the geometrics and other parameters, design parameters. There's at the physical level here, which is over here on the right side. You have many of you have seen this. I'm sorry, this is what we're going to be looking at in this class. Let's move over to the left here. You've seen this. What is this thing on the left here? What type of logic gate is that? Yeah, this is a buffer. This one's a buffer. Depending on what language depending on who you ask, sometimes people look at that as an inverter also. Okay. So let's assume that it's a digital inverter. Okay. What does a digital inverter do? Yes? That's right. So if you have a high voltage input, it gives a low voltage output. If you have a low voltage input, it gives a high voltage output. All right. So this is what it looks like at the block level. And if you go to the transistor level, this is what it looks like at the transistor level. There are two types of transistors that go into a digital inverter. There's the NMOS device, which is right down here, and then there's a PMOS device, which is up there. These are two different types of transistors. Was there a question here? Someone said something? Okay, I thought I heard something. So this is what it looks like in your Electronics 1 class. You look at how to make simple circuits using active elements, using transistors. In this particular course, we look at the physical level. We look at the NMOS device here, and we say, well, how do you actually build an NMOS device? And how many of you have seen the structure of an NMOS transistor or PMOS transistor from Electronics 1? Okay, so you have a little bit of an idea what the structure looks like. We go into more of the details of the device here. So the NMOS device is actually made out of a semiconductor, in most cases silicon, and there's a P-type silicon, which has more holes than electrons. There's N-type silicon, which has more electrons than holes. You have these different P and N regions. You have something called a gate region, a source and a drain. So all these different parts of a transistor are the things that we will talk about in the later part of this course. Before we do that, we actually have to have an understanding of just general semiconductor theory. So in terms of why this is important, well, if you do electronics design, there are going to be teams of engineers working at different levels. Okay, you're going to have the logic design team that works at the system or block level. And then you're going to have the another circuit design team that works at the transistor level. And then you're going to have the process engineers that work at the physical level. Right? So the reason why our curriculum has classes in all these three areas is because in order for you to be a good engineer, you really do have to understand all the levels of the hierarchy that goes into electronics design. And this process is often iterative. So I mentioned there's the circuit designers and there's the process engineers. The circuit designers will design digital and analog circuits. They'll validate them using not just hand calculations, but computer models. So, like things like PSpice. You guys have used SPICE and Multisim in your previous classes. So people work at that level, and then the process engineers are the ones who actually manufacture the semiconductor device. They characterize the semiconductor material properties and the device parameters. So have you guys done multi-sim simulations for MOSFETs? Do you remember that in those simulations you have to put in parameters like what is the Kn of the transistor, what is the oxide thickness, or the width and the length of the transistor? Did you put in any parameters? Okay, I have one person is saying, well, when you do these types of simulations, you have to put in some transistor parameters to describe how the device is going to operate. The process engineers are the ones who actually figure out what those parameters are, and they give these material properties and device parameters back to the circuit designers. And the circuit designers then make accordingly, they make changes to the circuit. And so this whole process happens sort of happens iteratively. Second thing that we were talking about, modern electronics. So modern analog circuit design exploits semiconductor phenomena besides the basic BJT and MOS equations. Things like short channel effects in MOSFETs makes it difficult to make transistors smaller than they already are. Let me move ahead here. Have we seen? Yes, Moore's law. Have any of you seen this chart? Those of you who are in my other class have seen it because I showed it yesterday. This is a famous chart. It was made by Gordon Moore, one of the guys who eventually founded Intel Corporation. What it's showing is the number of transistors on a microprocessor. You know, the microprocessors, those chips that go into your cell phones and your laptops, they're mainly composed of NMOS and PMOS transistors, the two of the devices that we'll be talking about in this class, which are, you know, they form logic gates, and logic gates eventually make a microprocessor. So there's been a trend since the 1970s. The first commercial microprocessor, one of the first ones, was the this one over here. It's the 4004 processor made by Intel. And that processor had 2,300 transistors on it. The speed of the processor was 108 kilohertz, the clock speed. And the amount of RAM was 640 bytes. And the size of the transistor, the physical dimension of each NMOS and PMOS device was about 10 micrometers. Now, to give you an appreciation for what 10 micrometers is, if you took the diameter of your hair, the diameter of your hair is 100 micrometers. So 1/10 of that is the size of the transistor back in the 1970s. Now, just by the 2000s, the size of the transistor had shrunk down to, as you can see here, 0.18 microns, 200 times smaller than what it was in the 1970s. There's two things that happens when you shrink down the size of a transistor. Does anyone read about this by chance? Just for trivia. Yes.
A little bit. As they shrink, the amount of heat is going to go up, and their issue burn out.
Okay.
So that's one issue. The other is because the channel that your electrons are moving across gets smaller and smaller. They start accidentally jumping because there's not insulation from the air. And I think that's what you're talking about, the microchannel effect.
Yes. So you're talking about the short channel effects, and you're also talking about the heat dissipation issue. Those are really good points, and those are actually, in fact, two negative issues that come up when you shrink the transistor down. So this is exactly what I'm talking about on the previous slide, that one important thing about understanding semiconductors is that understanding these second order effects that happen. So those are negative effects. How about positive effects? Like what are the benefits of making a transistor smaller?
Faster.
It's faster. That's one of them. The transistor becomes faster. And I saw another hand. I'm sorry?
You can stuff more in one IC chip?
Yes, exactly. Those are exactly the two things I was looking for. If you shrink a transistor, it makes them faster. And the reason why is because if you imagine electrons moving through a transistor device, The smaller you make it, the faster it can move through the device. Okay, you can think of it in that way. You can also think about it in terms of parasitic capacitances, but we'll get to that later. Second thing is that you can fit more and more transistors on a chip. So in terms of what that does to the microprocessor, if we look here, the speed issue. In 1971, the clock speed was 108 kilohertz. That's how fast the CPU would go. Now the clock speed is, back in the 2000s, it was 1.8 gigahertz. And I imagine that right now, like if you buy a laptop, it's somewhere around 2 or 3 gigahertz. Is that about right? Okay. And if you compare the second thing, if you compare the number of transistors, 2,300 transistors on a chip back in the 1970s, and if you go down here, you can see that we have about 40 billion transistors on a chip that was in the 2000s, and even more now. There's more than 100 billion transistors on chips now in some of the latest processors. In some cases, more than 1 trillion transistors. All right? So if you cram more transistors on a chip, what does that do to the ability of the chip? If you're able to cram more transistors on a chip, what does that do to the abilities of the microprocessor? I heard a few things.
Faster processing times, more computational power.
More computational power, exactly. You can do more complex calculations the more transistors you have in your chip, because you have more logic gates, more computational units. So, like these latest, when you hear about these like multi-core processors, quad-core, octa-core processors, they actually have multiple computational units on the same chip because they're all working in parallel. So it's like having 8 people working together to solve a problem instead of just one. So you get more computational power and the speed of the processor goes up. Okay, so if you look from the 1970s until 2004, between here, okay, you'll see that the number of transistors on a chip increased from 2,300 to greater than 10 million. And this happened if we graph the number of transistors on a chip like this over time, it's actually a nice curve like this. And this is what Moore's law is all about. So Gordon Moore predicted that we would be able to shrink the transistors in a fairly, repeatable manner. Every few years, we would be able to shrink the transistor enough so that you could double the number of transistors on a chip he predicted every 18 months, every year and a half that this would happen. Instead, what happened, it ended up doubling every 24 months. Okay, but still, I mean, this is quite remarkable, right? Every 2 years, we could double the number of transistors we had on a chip, more computational power, faster processors. And this trend continued for more than 30 years. Right now it's starting to sort of level off. The reason for that is at some point, your transistor becomes so small, it becomes almost the size of individual atomic layers. And when you make it that small, you start to see other effects. You start to see second-order effects. You start to see problems with short channel effects, where the MOSFET, if you're using it for as a current source, it doesn't behave reliably as a current source. There are things like hot electron effects. There are things like heat dissipation issues. If you have so many transistors packed into a small area, it generates a lot of heat. That's one of the big problems right now with microprocessors that the scientific agencies all over the world are really trying to solve. How can you remove the heat from the microprocessor? How can you make microprocessors that consume less power and generate less heat? So these are all modern issues that, in order to understand these, you really need to have a basic understanding of semiconductors. A few examples that I had written down before: short channel effects in MOSFET, and then sub-threshold CMOS for low voltage processors. Usually we think of operating you guys have learned the equations for threshold voltage. Above the threshold voltage, the transistor is on. Below the threshold voltage, the transistor is off, right? Well, a lot of processors, low voltage microprocessors nowadays, they actually use the sub-threshold region where the transistor is operating in that region instead of just in the on and off. The reason to do that is that you're using lower voltages. Instead of using a 5-volt battery, you can get by with using a 1.5 1.2 volt battery. Okay, the advantage of that is that it consumes less power, right? And you can use smaller batteries. So these types of low voltage processors, like the Intel Atom processor, are used in where you don't need that much computational power, but power efficiency and battery life is of supreme importance. Okay, so those types of processors are used in basic mobile phones and some types of tablets and so on. Okay, there's a lot of study right now in the trade-off between performance and battery life. There's various types of integrated circuit issues like latch-up, but those are those are some earlier problems. There's other problems like speed and power dissipation right now in high-performance circuits. Let's see here. So what else? So all these things, they do require an understanding of semiconductor physics. Getting back to Moore's law, so an example of what Intel did, they started shrinking their transistors. They did that for 30 years, and they got drastic improvements, and Intel made a lot of money, and they're still one of the most successful companies around. At some point, it was difficult for them to shrink transistors just in a straightforward fashion because of these things like short channel effects. And they actually had to go to new and radically different transistor designs. An example of that is this thing called the Finfet. This is the type of transistor that Intel is using right now. For those of you who have seen the structure of a typical transistor, it looks something like this. You have the gate here on top, you have the source, and then you have the drain here, and then you have the gate, the dielectric right there. So, this may look familiar to some of you. Let's see. And this device here on this side, I don't know why this thing is not working very well. There we go. On this side, this is what is being used right now. Notice that you have the semiconductor material in the middle, and the gate goes all the way around the device. So this is called a Finfet because it looks, the semiconductor material looks like a fin sticking out of there. By having the gate go around all three sides of the semiconductor, you have more control over when the transistor is on and when it's off. Okay, so Intel had to go to this very different design after doing this design here on the left for more than 30 years. So again, it's important for you to understand basic semiconductor devices in order, as these designs mature further and they start to go to other types of devices. These are some images of the tri-gate transistor. This is from 2011, but this is what's used in a lot of the commercial ICs right now. This device right here, you can see the dimension, 17 nanometers, incredibly small device. 17 nanometers, like, it's only a few atomic layers thick, really. That's how small the transistors are nowadays. And these are more images of what the tri-gate looks like. You can see the gate material sort of going around here like that. Any questions so far? All right. Another cool example of a new device is the Memristor. The Memristor was a new electronic device component that was discovered in 2008. And it was actually a very exciting scientific discovery. And now HP, just 2 weeks ago, I heard that HP is developing a new computer called the Machine. Has anyone read about this article? One of you can do your presentations on this. It'll be pretty interesting. HP designed and discovered this new device called the Memristor, and they're making a new computer based on it. And supposedly, this new computer is going to have properties that it may have like only 1% the power consumption of traditional the server computers that are used by things like Google and Facebook. 1%, so 99% reduction in power consumption. if it works. So it's going to be a new computer that uses a memory that's based on memristors instead of DRAM and SRAM, which is what is typically used. So what is a memristor? It's a theoretical mystery passive circuit element that relates magnetic flux to charge in the same way resistors relate voltage to current and capacitors relate voltage to charge, and inductors relate flux to current. This chart, this sort of plot here shows this. You don't need to know this for the test, by the way. This is all for your own interest and enjoyment. Well, the stuff that's going to be on the test will be covered later. So just relax and you can just think about some of these concepts here. In your Circuits 1 class, you learned about resistors and you learned Ohm's law, V equals IR. Right? So the resistor is a component that relates voltage to current. That's here on the top left. Now, if you go here, you learn that the capacitor was something that related charge to voltage. There was this relation Q equals CV for a capacitor. Right? And if you look down here, the inductor relates magnetic flux to current. Okay, if you remember from electromagnetics class, and then theoretically there should have been this fourth element which relates magnetic flux to charge. So this element was predicted to exist back in the 1960s and 70s by a famous researcher at Berkeley, but the device was never made because there was no way to make it. And in 2008, Hewlett-Packard used semiconductors. They used a titanium dioxide thin film with doping and with the doped and undoped region. They were able to make this theoretical mystery element, and so they were able to make it using semiconductors. So resistors, capacitors, and inductors, you don't need semiconductors, but for this fourth mystery element, you actually have to use semiconductors to do that. And so it turns out that this is a very exciting element because it has applications in very high density storage and in learning networks. It can actually remember its own state, so it can act as memory. So right now, HP is making memory units out of memristors. They're expected to be released in 2016, 2017, and they have a large team of people who's actually working on a computer based on the memristor. You may hear about that in the next few years. There's also new and exciting solid-state devices in other areas. I would say in the last 5 years, something that has been at the forefront of our national interest, international interest is solar energy. Obviously, you all know about the energy crisis in terms of our use of fossil fuels and carbon dioxide in the air, climate change, and so on. So one of the nice things about photovoltaics is that they can convert sunlight directly into electricity. And there's a lot of interest in increasing the efficiency. On a bright sunny day, the sun provides 1,000 watts per meter squared. Think about this. If you had a 1 meter by 1 meter area, maybe the size of this platform here, on a bright sunny day, that can generate 1 kilowatt. 1 kilowatt of energy. That's a lot of energy. But previous generations of photovoltaics can only capture about 10% of that energy, so about 100 watts per meter squared. All right, one of the big areas of research in semiconductors, because photovoltaics, by the way, they are semiconductor devices. They are actually they're like p-n junctions. There's a p-type material and an n-type material next to each other, and when light hits a semiconductor, it generates electrons and holes. And without going into all the details of it, that ultimately generates the current in the semiconductor. Photovoltaics are semiconductor devices. So there has been a lot of interest in the last 5 years in improving the efficiency of semiconductors in being able to capture sunlight. One of the areas that's been under very intense scrutiny and research is how can we capture different parts of the solar spectrum. Silicon the semiconductor of choice, the silicon is widely available on Earth, it's very abundant, and all of the manufacturing technology right now is based on silicon. So silicon is definitely the cheapest and most economically scalable material, semiconductor material there is. However, silicon is only good at capturing a small portion of the solar spectrum. The spectrum meaning like here on the x-axis you can see we have wavelength. Right, the sunlight is coming in at all different wavelengths, right? There's some ultraviolet light, there's infrared light, there's visible light. Silicon is only good at capturing visible light. So this part of the spectrum, 600, about 400 to about 800 nanometers. Okay, we'll talk about why that is later. It has to do with something called the band gap. So there's a lot of interest in designing other semiconductor materials which can capture this portion of the spectrum, the infrared region of the spectrum, and capturing maybe even some of the ultraviolet region. Most of the interest is in infrared. The ultraviolet, we don't get that much ultraviolet light here on Earth. Does anyone know why? It's absorbed. Yeah, exactly. It's absorbed by the ozone layer and by the atmosphere. Right. But infrared light comes through. And while silicon is very good at capturing visible light, it's not really good at converting infrared light. There's a lot of solar energy in infrared light. So developing new types of semiconductor materials which can capture infrared light is one of the areas of interest, for example. Another area of interest is how can we manufacture semiconductors so that they're much cheaper? There was a lot of interest back when I started my job here, like around 2009, 2010 timeframe, is to make printed solar cells. So instead of using the traditional hard solar cells, you can make solar cells that you can print out in large rolls, roll by roll, much like newspapers are printed. If you could do that, then presumably solar cells would become much, much cheaper. So it became a trade-off between, those printed solar cells were not as efficient as the traditional solar cells. So it's often a trade-off between cost versus efficiency. So there's a metric called the cost per kilowatt hour. That's a very important metric in photovoltaics. All right, the importance of photovoltaics, I don't really need to state much on that. You know that eventually that the world is going to have to reduce its reliance on fossil fuels and have renewable energy. So Japan, for example, expects 20% power from renewables by 2020. China and U.S. recently signed a pact, and that was saying that by 2050, I think China was also going to have 20% of its renewables 20% of its energy from renewables, and the U.S. has been looking at the same. Google was one of the first companies to put massive solar panels on the rooftops of its big data centers. This was back in 2005, so about 10 years ago. Now you see solar panels on certain parts of California. Every rooftop, every home will have solar panels on top of it. One of you guys was from LA, right? Who's from? Yes. So you've seen some solar panels on rooftops there. We don't have as much here in Michigan just because it's more cloudy here in Michigan, so the economics make a little bit less sense. But if you go to Phoenix or Southern California, a lot of homes have solar panel installations. When the cost of solar panels comes down, we'll expect to see that here too. In places like Germany, they have gigantic solar farms where they have like plots of farmland that have been cleared off, and they have massive arrays of solar panels there. We have these too in the middle of the desert. We will expect to see more of those. So that's a very important area of semiconductor devices. Another nice thing, semiconductor devices are used in cameras, in displays. So most of you obviously have, like smartphones, and you have. Oh, by the way, how many of you have a smartphone? How many of you own like an Android smartphone or like an iPhone type thing? Okay, pretty much everyone. Okay. I was just curious because I was gonna experiment with something this term, like giving quizzes through. I think Blackboard has this thing where you can send quizzes and you can do your quizzes from your phones in class. I thought I'd try it anyway. I just wanted to ask. Anyway, so if you have smartphones, then your smartphone most likely has a camera on it, and then there's obviously larger cameras like DSLRs and things like that. The light sensors in your camera, the thing that actually takes the image, what takes place of film, what film used to be, is a CMOS sensor. It's made from silicon. There's two types of sensors. There's something called a charge-coupled device sensor, CCD, and there's also something called a CMOS sensor. I won't go into the details of what they are, but suffice to say they are both semiconductor devices made from silicon. And you can get sensors that are very large, like this big. These are the kind of sensors that go into digital SLR cameras, like the big ones that you see, wedding photographers using. And they can be as small as, just like maybe about this big. So those are the types of sensors that are used in your cell phone cameras. They have different performance. The larger sensors typically have less noise, so they give better quality photos. Smaller ones are good for more portable applications. But CMOS sensors, they provide a very efficient and fast performance in capturing RGB light. What is RGB? Red, green, blue, right. We got lucky because it turns out silicon is very sensitive to visible light, red, green, and blue, the same types of wavelengths that we see with our eyes. Okay, so silicon is a very good material for making optical sensors. I would say that high-performance CMOS sensors have revolutionized digital photography, and the picture quality has become to the point where it's superior to film. Most of you don't remember film anymore, but when I was younger, we did have the film cameras, and you had to be very careful with, if you're going to take a picture, you're going to make sure that the picture is right because, paying the film, it wasn't super expensive, but it was expensive enough where, you don't just take 100 pictures of the same thing and then just later decide which one you're going to keep. And that's what I do right now, and my whole hard drive is filled up with junky pictures, and only 1 out of 10 is good. But anyway, it used to be like the early CMOS sensors, the quality was never as good as film, and so film photographers always said, no, we must stick to our film in our dark rooms. But nowadays, I would say pretty much the whole field has pretty much sticks to CMOS now. And instead of working with a dark room, where you can manipulate your photos there, you use things like Photoshop and things like that. So that's one industry that was completely revolutionized by CMOS. Of course, the computational industry is another one. But another example here is display technologies. This video here shows a Sony flexible OLED display, but I probably don't even need to show these to you right now because some of these things are, you can go to Best Buy and take a look at it. OLED stands for organic LEDs. And does anyone know what LEDs stand for? Light emitting diode, right. It's a type of diode that emits light. LEDs are not made out of silicon. They're made up of a different material called gallium arsenide and gallium nitride, gallium aluminum arsenide. Different semiconductor materials emit different color light. And even 20 years ago, it was difficult to find LEDs of different colors. Now they're widely available. Every color you can imagine, there's an LED for it. They've also become cheaper to manufacture. And this particular OLED displays are what's called organic LEDs. They're made up of materials that you can actually print with ink. You can get a semiconductor ink, and you can print that on a flexible film like a plastic sheet. Okay, and that sheet can become a display because it's filled up with light-emitting diodes. All right, so you can see a picture of this up here, or you have you can have these essentially like flexible displays. Does anyone own a one of those Samsung Gear watches? No, I saw one of those recently. One of the applications of these flexible displays that you're going to have like watches and things that you wear on your wrist. And it used to be that the displays always had to be rigid and flat, but now you're going to have displays that bend around. There are new mobile phones that have curved displays on them. I think it's called the Samsung Curve. Samsung also has TVs that they've released. They're sort of gimmicky. I don't know how really useful they are, but they're TVs that have curved displays. OLEDs are going to make displays pretty much ubiquitous. You might see displays on windows. Eventually, you'll see displays on heads-up displays on cars if the regulations allow. Because this type of technology, you can literally print out displays using a printer. You don't need the expensive processes that you need for some of the previous generations of TVs. So we're going to see a lot more changes with that as time goes on. Another big thing is solid-state lighting, and this has already become quite ubiquitous. Actually, you know what? I realize we're a little bit ahead here. Why don't we let's take a 5-minute break and let's come back to this. Yeah, let's take a 5-minute breather. We'll come back. All right. So solid-state lighting. So we're talking about the different, I guess, important areas more recently. I'm just giving you a small sample of some of them. Solid-state lighting is another important problem. 1/3 of the U.S. energy consumption is for lighting. And the U.S. and China are the two largest energy-consuming countries in the world. So 1/3 of our power is coming from lighting, and the other big chunk is coming from heating. And I guess we have to solve that problem as well. So with regards to lighting, solid-state lighting uses 66% less power than comparable incandescent bulbs, resulting in a 10% reduction in the overall energy usage in the U.S. So incandescent bulbs, you know, the old-style light bulbs, you know, they look like this, the light bulb. So I don't know if you can see here, but inside one of these light bulbs, there's a filament. It looks like that. It's just a resistor, really. And the reason why there's a glass bulb around there is because that whole thing is in vacuum. So that filament, actually, through some process called thermionic emission, it releases light when you run a current through there. However, the process is not really that efficient. I think the energy efficiency for an incandescent bulb, oh yeah, it's over here. Here's my laser pointer. Incandescent bulb, 10% efficiency. So 90% of the energy is being converted to heat, you know, joule heating when you run current through a resistor. This is one of the reasons why those types of bulbs used to get very hot. You know, if you've ever touched a 100-watt bulb, you'll remember that. So the next version of that, not really a next version, something that came out about the same time was a fluorescent bulb, a little bit later than that, actually. These are fluorescent bulbs, the kind of bulbs that we have in these lamps. The way fluorescent bulbs work is something fundamentally different. You actually have a tube. And you don't really need to remember any of this stuff, but it's interesting trivia. You have this long tube like this, and it's filled with the gas. And when you put a voltage source across here like so, it creates a discharge. I'm trying to draw a lightning bolt, but get the idea. It creates a discharge within the tube. And that discharge is really giving off, it's a spark. Think about it like a spark, and it gives off ultraviolet light. The ultraviolet light we can't see, it's harmful to us, and it wouldn't be very useful to us. But what happens is that there's a powder coated on the surface of this, on the tube. That's why many of the fluorescent bulbs, they appear frosted white, and they have some powder coating on them that absorbs ultraviolet light and it emits visible light. The ultraviolet lamps that you can find in a tanning salon are basically like basically with the powder removed, right? And you know, you can use that to burn your skin and get skin cancer. Fluorescent bulbs are 30% efficient. Okay, so they're actually quite a bit more efficient than incandescent bulbs. That's one of the reasons why at Home Depot and all the other places right now, most of the bulbs that you can buy right now are fluorescent bulbs. It used to be that fluorescent bulbs gave off this really nasty, like bluish color that made you look like several years older than you were. But now the phosphors, that powder, that coating that they put on the tubes have gotten better to the point where they emit light that's similar to what you can get with the incandescent bulbs, the traditional bulbs. And you can get phosphor coatings that give off sort of a bluish light, which is good for studying, or sort of a yellowish light, which is good for gives a more warm glow, so on. But the most efficient energy source is the LED lighting. So the LED lights are 45 to 65% efficient, so almost 50% better to twice as better as 50 to 100% better than fluorescent bulbs. This is why a lot of places you're starting to see LED lighting pop up. You can probably buy LED lamps at Home Depot right now, Lowe's. They're more expensive, but you can buy them. And once you buy an LED bulb, they will really drastically drop your electricity consumption from that light bulb. And they last a very long time. LED lighting typically lasts 100,000 hours or more, because you will not have to replace the bulb very often, if at all. Also, LED lighting is available in, you can get red, green, and blue LED lighting, and by combining RGB, you can get white light. And so you can get very nice white-colored LED lighting. This is, you'll find them in cars. You'll find them, I think Mercedes or BMW was the first company to use LED lighting in their headlamps, and now other car manufacturers use them as well. If you walk around cities like Ann Arbor, you'll see that they have LED lamps on the streets, and there's solar panels on top of them. So they're not even attached to the grid. They just have a battery in there, and they're very efficient. The LEDs consume so much less power than incandescents that you can just charge it using solar power during the day and run it during at night. It's very sustainable. This is an old article, but as an example, like if Anchorage installed 16,000 LED streetlights, because in Anchorage they have 6 hours of daylight now, and even when it's daylight, it's kind of like it looks at dawn, like the light is just at the horizon. So a place like Alaska, which uses a lot of lighting, they end up saving $360,000 per year after installing the LED lamps. So what's going on in this field right now? There's a lot of interest in making the LED lamps even more efficient, number one. And number two, making them much less costly. Because one of the initial arguments against LED lighting, well, okay, they're more efficient than incandescents, but that bulb costs like $20 or $30. So how can we bring the cost of that bulb down significantly? And people are looking at using, similar to photovoltaics, they're using printed and organic materials to bring down the cost of LED lighting, new manufacturing technologies, and so on. LEDs are obviously made from more exotic materials than traditional incandescents. They use materials like indium. They use gallium arsenide, not gallium arsenide. Indium, gallium, and nitrides. These kinds of materials are used in these types of bulbs. And those types of materials, those types of metals can't be found everywhere in the world. So places in the world that have indium supplies, they're doing really well right now. So there's an interest in finding different semiconductor materials that can be used for lighting applications. Nanoelectronics is an emerging field. I mentioned that the Moore's law has kind of come to an end, and we can't just improve transistor performance just by making it smaller. So there are many research groups who have been looking into fundamentally new ways of creating electronic devices and electronic computational devices, and also electronics for other things like wearable sensors and displays and so on. Two of the most well-known or well-publicized are these things called carbon nanotubes here. Carbon nanotubes is like carbon atoms, like a ring of carbon atoms. like this. So it forms a tube, and it turns out that these tubes have the way that electrons flow through these carbon nanotubes, they can move through the tube with a very fast velocity. So they have a very high mobility, much higher than traditional materials like silicon, where electrons and holes, they bump into other atoms and it slows them down. Another material with very high mobility is graphene. Graphene, instead of being where the electrons are moving in a one-dimensional space, the electrons are moving in a 2D space. So this is a sheet, a two-dimensional sheet of carbon atoms. It's literally one atomic layer thick. Also has a very high mobility. I always mention this one. We have Professor Mark Cheng in our department. Most of his research program is using graphene for various types of applications, ranging from energy storage to biomedical sensors and so on. So if you're interested in working with new types of semiconductor materials, he's a good person to talk to. Yes?
How expensive is something like graphene?
Graphene is actually, when it's made, is actually quite cheap because it's made from carbon. And carbon is a very abundant element. The question is, how can you arrange carbon in a single sheet like they do with graphene? And there are ways to do that using chemical vapor deposition, other ways of doing it which are less expensive. The people who won the Nobel Prize for graphene, I think I was talking about this in my other class. Yeah. I'm trying to remember which year. I think it was around 2009. 2009 is when they did the work, and they won the Nobel Prize, I think, just a couple years later, which is unheard of. As another example, like people who did work on the LED. There was a scientist by the name of Nakamura. He did the work in the 1980s and early 90s, and he just got the Nobel Prize last year.
Yeah, for the blue LED.
For the blue LED, that's right. That's right. And the person who invented the first LED, which was infrared or red color, he felt like he got shafted because he felt like he should have gotten the Nobel Prize, which is I kind of agree. I mean, but the point is, like, these things were people end up getting the Nobel Prize literally like decades later, when they're maybe too old to appreciate it. But the people who did graphene, they literally got the Nobel Prize a couple of years later. And the funny thing about them, the great story is that their experiments with graphene use Scotch tape. So they had a pencil like this, right? The tip of a pencil has graphite. They don't use lead anymore. They use graphite. Graphite is carbon. So they took a piece of Scotch tape and they removed a single layer of the graphite, and they transferred that layer of carbon atoms to another thing, and that's how they did their testing. So Scotch tape won them the Nobel Prize. Remember that. Great story. It pissed a lot of people off, but anyway, it's how you do the science rather than how sophisticated your lab is. Materials like graphene and carbon nanotubes, they've been under a lot of interest because there's a lot of studies of how electrons transport through these materials. In one-dimensional and 2D materials, they travel fundamentally differently than electrons travel through traditional three-dimensional materials. Things like silicon and other traditional semiconductor materials are three-dimensional. These materials can be made very small, obviously, because they're only one atomic layer thick. And they also have other interesting properties. Like graphene, for example, is a conductor. We usually think about conductors as metals, right? Well, graphene is flexible, and it's also a conductor, and it's also transparent. Imagine having a transparent conductor. Right? So there's a lot of interest in putting graphene on displays, on the backs of TVs, the back panel of TVs, instead of using metal wires. There's a lot of interest in graphene for biomedical sensors, things that you can wear, like flexible displays and flexible things that you can wear. Graphene is also very biocompatible. So there are these new emerging materials that are coming out, which are quite interesting. So the field of solid-state devices really is wide open. Here's an example of flexible electronics. These aren't using graphene per se, but they're using some semiconductor materials. This particular picture here is just using regular metals, but here you can see they're using some type of semiconductor materials, in addition to traditional metals. There's a lot of interest in making semiconductors flexible. Traditionally, microprocessors are made on rigid substrates. If you can make semiconductors on flexible substrates, then you can put them on your skin. You can bend them, like you see here. You can make semiconductors in round substrates. What you see here is a prototype for a retinal prosthesis for people who are blind. This is like an eyeball here. And in the back here, you can see some of these semiconductors and metal traces in the back. The semiconductors, as I mentioned, they can serve as light sensors. So it's like you're putting a camera in the back of your retina. And they've actually done some work with this. There's a company called Second Sight. Look them up. It's pretty awesome. They're actually working on a retinal prosthesis for people who have been blind their whole life. They're starting to see for the first time. It's quite amazing. So an implant like this requires a flexible substrate. You can't put a rigid semiconductor into the back of an eyeball. You need something that's curved. So this is an example of where flexible electronics is very useful. So about 2 years ago, the NSF, the U.S. National Science Foundation, was putting a lot of money into flexible electronics, and they still are quite interested in it. Biomedical sensors, a lot of semiconductor devices are used in various types of biomedical sensors. This is just one example. Have any of you used this app called Izumio? It's a heart rate monitor app. Some of you have it on your phones. Those of you who don't, if you own a smartphone, download the app. It's pretty cool. You can. It uses a camera on your phone and the flash on your phone to measure your heart rate. You just put your finger on there. It measures heart rate. So try it out. Yeah, I can see her. It's trying it in the back there. It's pretty fun. That's an example of where semiconductor devices are being used for health applications. Our group is working on a heart rate sensor, like a wearable sensor that you can wear on your earlobe. So it's like a small earring, not much larger than a dime that you can wear on your earlobe, and it'll constantly monitor your heart rate and send the information wirelessly to a cell phone. That's something that we're working on. There are other types of heart rate monitors like the chest straps and so on, which we think are a little bit less convenient. But these are all semiconductor devices. Semiconductors are used in the sensing, the data collection, and also the wireless data transmission to the smartphone. And the smartphone itself, of course, is basically like made up of a whole bunch of semiconductor devices. This is one of the emerging areas is how can we do biological sensing with semiconductors, and how can we create this type of infrastructure? This chart on the bottom here sort of gives you an idea of what this whole field of mobile health is about. The mobile health is the idea that instead of having all your doctor's procedures and diagnostics done at a hospital, that you'll be doing them at home or even like through your smartphone with various types of very small microelectronic devices. And some examples are out there already. You can think of things like Fitbit that does activity monitoring. There are heart rate monitoring watches right now that you can buy. There's something called MyBasis, a company called MyBasis that makes a watch that monitors your skin impedance, which correlates to stress levels. There's home blood pressure monitoring devices. There are semiconductor devices that are used for monitoring blood glucose for diabetics. So the idea is that at home you have these wearable devices for monitoring various physiological parameters. These devices send data to your cell phone or computer, and then these send them along to central servers where your electronic medical record resides. And so this information can be made available to medical personnel and family and so on. The idea behind this is that the more data that can be gathered on your health, that this data will be fed back to you as a patient, and it can help you make adjustments in your lifestyle, whether it's to reduce stress, reduce blood pressure, or whether to eat certain types of foods at certain types of day to basically manage your own health. And it's expected to become very important in the next few decades because the cost of healthcare in the U.S. is quite high, and the overall health of Americans has actually decreased over the years, just due to the various types of foods and lifestyle things that are going on. So there's actually a lot of interest in using semiconductor technology and other like sensor technology to help improve the overall health and improve the medical system here in the U.S. and all over the world, really. I'm going over a lot of different things. Any questions so far? Okay. So this is always something fun to do. When we talk about semiconductors, probably the biggest impact that semiconductors have in your life is in your smartphone. I have a couple examples here, but can you think of how many semiconductor components does your smartphone have? So let's just think about this for a minute and see if we can come up with a list here. All right, what's one example of a component? If you open up your cell phone and just wanted to count the number of semiconductor components in there, let's do that. What's
the screen is a sensor.
the screen? Okay. The screen is made up of like my phone, for example, which I've had for a couple of years. It's the Samsung Galaxy, quite a popular phone. It has an OLED display. Organic LED. So it's a very efficient light emitting device. The screen quality is actually very good, much better than the traditional LCD panels. All right, the camera. So we just talked about in this class that the camera is a CMOS sensor, which the way that a CMOS sensor works is that when light hits the semiconductor, it generates electrons and holes, and those electrons and holes can actually be measured. We can measure how many electrons and holes were produced, and that gives us an idea of what the light intensity is. That's what happens in one pixel of the image. A CMOS sensor typically has 5 million pixels. If a 5 megapixel sensor has 5 million of those individual pixels. So the obvious advantage is that we can make those pixels very small, and the more pixels we have, the better the resolution of the image. So yeah, the camera. What else?
The microphone or like the speaker?
I'm sorry?
The speaker?
Well, the speaker is actually more of a mechanical device. The speaker is kind of like vibrating back and forth, and that's
But
giving
when
the
you
image.
talk to it, like
The microphone.
microphone.
The microphone. Now, the microphone, this is actually what's called a MEMS device. A MEMS microphone, it has a moving part in it to convert the vibrations into an electrical signal. And then there are actually semiconductor components on there to pick up that electrical signal and then process it into something that can be stored on the device or amplified. Yes.
I don't exactly know the name of the sensor, but there is one more which is next to the front camera, where the
light sensor.
yeah, the light sensor.
Yes, those are called proximity sensors. Now, proximity sensors, they're also called light sensors. These sensors basically, they are also CMOS. Or, I'm sorry, these things are actually photodiodes. So the photodiode is basically a diode that senses light. It's very similar in structure to a solar cell. When you put the phone in your pocket, the display turns off automatically. So that's the function of the light sensor. It also, it adjusts the brightness of your display, automatic dimming.
Or usually when you take it next to your ears, when you are talking, it's also on.
It turns the display off. Yeah, exactly. So there's a light sensor, and there's also they're also called proximity sensors. They can detect how far you are away from an object. Those are also done with semiconductors.
Microprocessor.
The microprocessor, of course, the brains of the device. Microprocessor. This is a CMOS device made from silicon.
Memory.
The memory, yes. The memory and the hard drive. Memory and the hard drive. This is also CMOS silicon, made from silicon.
Touch sensor. Touch sensor.
The touch sensor. You mean the button or the screen?
There's a touch one.
Oh, the button on there. Yeah, the button actually has some. It does have some sensing components in there. Now, I think in the Galaxy the button is just a mechanical button, but I think in the newer iPhones they actually have a biometric sensor in there, which is really cool. Really cool. Yeah.
Samsung too, it scrolls.
Yeah. Samsung,
Oh, the newer ones
the
have.
new one, yeah.
Even I think the 4.
No.
Oh, really?
Five,
No,
the
the
five.
is mechanical sensor.
Ah, okay. Yeah, I'll have to get the new one. And I was at Whole Foods the other day, and you can actually pay for your grocery bill with the iPhone 6 because it has a biometric thing on there. Really cool. Hmm?
The iPay.
Yeah, Apple Pay.
But the technology name is.
What else? I'm sorry?
It's been around for years.
The technology name is NFS.
It's technology is called what?
NFS.
Anafis. NFS. Oh, near field. Near field. Okay. Near field communication. Yes. NFC chips. Yes, we can add that in there. NFC chips. Also silicon. There's one very important part we've left out.
Wireless.
Connectivity. Yes, the wireless module. The wireless chip. This is also CMOS. So the important part, like the wireless chip, has a lot of amplifiers on board. Amplifiers are made from transistors, right? Some of the higher performance ones are made from bipolar junction transistors, and some of the less expensive ones, and actually some of the less expensive ones are actually more used now because as long as they can get the job done, it's good enough. You can make amplifiers just out of CMOS right now. No need for bipolar junction transistors. And not having bipolar junction transistors actually makes the device much cheaper. When I think there's a company called Atheros, I think is a company that started back from Stanford. They were one of the first companies to commercialize CMOS amplifiers. And once that happened, then Wi-Fi and 3G and 4G things were in every type of device. And you can buy Wi-Fi things and wireless devices for like, $10, $20. Costs less than groceries at Whole Foods. Yeah. You have a kid, you know.
They're still one of the cheapest companies too for buying Wi-Fi. Atheros is still one of the cheapest companies.
Yeah, and Atheros has their chips in many other commercial devices right now. So, wireless components. You can see, like, really, your smartphone really is just an amalgamation of different semiconductor components. And where would we be without our smartphones, right? So I'm trying to get this point, like, you would not be alive without semiconductors. You would literally die. We may have missed a few things here, but you get the idea, right? Really, the electronics revolution, like from the 1950s and 60s till now, you think about it. Many of you have heard this whole spiel before, but for those of you who have not, semiconductors were invented in the 1960s and 70s. Those are when the first processors were coming out. The 80s was kind of like the mainframe revolution, where like big companies and banks and financial organizations and research organizations who could afford computers would have roomfuls of mainframes, and they would be able to do some amount of computation. Today, the amount of computational power in your smartphone is actually more than those mainframes that took up the entire room. So in the 80s, it was a mainframe era. In the 90s, like people started having, it was a home PC era, the decade of like where everybody started to have PCs in their homes. Towards the end of the 90s with internet, starting with dial-up. Does anyone remember dial-up? I was playing. I discovered Doom and Warcraft. You know, when it was still on dial-up. It was like in 1997, and my friend and I would play like till late at night. And the problem. No, it was actually before Warcraft. It was Doom and Wolfenstein. It was like.
Yeah, 1997 would have been Warcraft.
Okay. Okay, you got the whole history.
Diablo 97 with Warcraft 2, 98 with StarCraft, and that's when Blizzard actually released games on time.
That's impressive.
The original Warcraft, I think, was like 94.
Well, I used to play games on dial-up, but the problem was, you know, whenever your dial-up connection went bad, you had to phone again, and there's like the middle of the night, my parents are waking up, and like they're like, "Why? Who's calling you at 2 a.m. in the morning?" Anyway, so late 90s was starting the internet, and the 2000s was wireless. Okay, you think about where semiconductors played a role. PC computing, mainframe computing was a microprocessor. Okay, like internet and wireless was when companies like Ethereum started to put Wi-Fi components using CMOS and made them very cheap and available. So wireless and amplifiers were all semiconductor components. And the whole mobile revolution right now, like the miniaturization and having all these different types of sensors embedded into your cell phone and sensors that you wear right now, they're all being driven by semiconductors. So if you look at the trajectory of semiconductors, slowly, it's really being pervasive in different aspects of our lives. And it'll be really interesting to see, you know, and some of the things I mentioned in class today, semiconductors are now going into other aspects of energy. Okay, health devices, lighting. You know, so they're really becoming even more ubiquitous than they used to be. So think about some of these areas. When you do your class presentations, like I said, you can present some interesting research and new types of semiconductor devices that's being done at the academic level. If industry is kind of where more of your interest is, then you can do you can talk about some new devices, so long as you talk about the specifics of the device. For example, don't do a presentation where you're just like, Samsung released a new a curved display TV that has 4K resolution and show some great pictures. While that's cool and it's interesting to many of us, I actually want to see some technical content. So you go into the details of what an OLED display is. How did Samsung make it? And it's, you need to have some meat in your presentation. So I hope that some of these areas kind of gave you a flavor for what's interesting in the semiconductor world right now. Next time in class, we will start on Module 1, Crystal Structures and Electronic Materials. And I'll see you all next week.